So, the planning approach is described so far they reason with states. So, we have been drawing figures where you have this state and then other state and so on, then you have the goal state and so on. The planner is basically looking at a state and a goal description which describes the state. If the state satisfies the goal description, then it terminates. Otherwise, it searches over the state space looking for actions to add to the plan. The plan only happens to be a byproduct of state space search essentially. Now, we want to shift our attention to only working with plans, and that is called as plan space planning. And here we consider the space of all possible plans and search in this space for a plan. We already got a flavor of this when we were looking at branch and bound with TSP. We said that look at the space of all possible tours, then keep refining the best tour till you have reached the solution. In a similar manner, here we want to look at the space of all possible plans. So, when we say all possible plans, it does not mean a solution, this thing, it just simply means a plan is a sequence of actions. So, any two actions in a sequence is a plan essentially, whether it is a solution plan or not is a separate matter. So, in the space of all possible plans, you will consider all sequences of actions and search in this space for a plan essentially. We call such approaches as plan space planning, because you are only searching from one plan to another. The search space in plan space planning, which we sometimes use PSP and sometimes we also say POP. POP stands for partial order planning. We tend to use the two names synonymously, plan space planning or partial order planning. The search space constitutes of partial plans essentially. So, what is a partial plan? A partial plan is a 4 tuple in which there are 4 elements A, O, L and B. A is a set of partially instantiated operators or actions in the plan. It simply says what actions are present in the plan. O is a set of ordering links of the form that AI comes before AJ. So, you are imposing an order on some actions in the plan, and that is represented by this set O, which is a collection of such ordering links. Then L is a set of causal links of the form that an action AI is linked to an action AJ through a proposition P, and we will refine this definition in a moment. We have said that they are partially instantiated, which means that we are talking about operators which have variables essentially, and actions we sometimes think of them as ground operators or operators without any variables. So, when we said for example, pick up x from y unstack x from y, we have not stated what is x, what is y, we treat them as variables. Now, in our representations in the style used in first order logic, we sometimes prefix a question mark to distinguish a variable from a constant. So, question mark x says that x is a variable, and if there is no question mark, it means that it is a constant. It is just a way of discriminating between these two. In some literature, you might find that people use x, y, z for variables and a, b, c for constants, but that will not help if you are writing a program unless you adopt that convention in the program. If you have looked at the language Prolog, for example, which also deals with predicates and variables, it has a convention that it treats capitalized words as variables and small lowercase words as constants essentially. So, some convention you have to adopt, and we will adopt this fact that we can use a question mark to distinguish a variable from a constant. So, the fourth element of this tuple is a set of binding constraints, which means what values the variables can take essentially. So, we can have various kinds of such constraints. We can say that x equal to y, or we can say x is not equal to y, which means it must not be bound to the same value. So, if x is a, y cannot be a, or you can say that x is a, or you can say x is not b, or you can even say that x comes from a subset of all the let us say blocks in this case, and it must be one of them essentially. So, some kind of binding constraints that if there are partially instantiated operators in your plan, what are the constraints on the variables in those partially instantiated operators. So, let us look at this in a bit more detail. The constituents of a partial plan are these 4 elements A, O, L, B, where A is a set of operators, partially instantiated operators. We have used A because A also stands for actions. O is a set of ordering links, L is a set of causal links, and B is a set of binding constraints essentially. So, A is a set of partially instantiated operators in the plan. It simply identifies the action that are somewhere in the plan. It does not say it is the first action or the second action or the last action or something like that. All the approaches that we have seen construct plans in some particular order. Forward state space planning constructs plans starting with the first action. Backward state space constructs plans starting with the last operator. So, the first action they add is the last action that will be there in the plan. In partial plans or in partial order plannings or plan space planning, we do not say that. We simply say that somewhere in the plan that action is occurred, and we say partially instantiated because, for example, as shown here, you are saying that stack A onto something. We have not stated what essentially. For example, this could be done because you wanted the arm to be empty, and the arm was holding A essentially. So, as we said, O is a set of ordering links of the form AI comes before AJ. So, this is how we write this. AI comes earlier in the order than AJ, and the partial plan is thus a directed graph. It imposes order on some actions of the plan. Whenever we are sure that some action should come before another action, then we add an ordering link to the partial plan, and that is put in this set called O. Then we have this set of causal links. They are of the form AI, which is an action, P, which is a proposition, and AJ, which is another action. The causal link AI, P, AJ represents the fact that action AI has a positive effect P, as written here, which is a precondition for AJ essentially. So, AI produces a predicate or a goal, and AJ consumes it. So, we say AI is the producer of P and AJ is the consumer of P. So, this causal link tells you how that precondition for this action AJ is achieved essentially, and it is achieved because there is another action AI which produces P. So, obviously, AI must come before AJ, it has to produce P which AJ will consume. So, whenever you add a causal link, you also add a corresponding ordering link saying that this action AI must come before action AJ. And the binding constraints we have already discussed, that they tell you what values variables can take essentially. So, plan space planning always starts with one initial plan, which is the same. So, if you have a planning problem, remember that a planning problem is described by 3 things. One is the start state, one is the goal description, and the third is the set of operators available to you. So, let us say start state has S1, S2 up to Sn, these are predicates which are true in the start state, and G1, G2 up to Gk are predicates in the goal state that you want to be true essentially. So, that is the planning problem given to us. What the initial plan in plan space planning is that it always begins with an initial plan which is described as follows. There are 2 actions in it, one is called A0 and one is called A infinity. So, or one is the first action and the other one is the last action in the plan, and obviously the first action must occur before the last action. So, we add that ordering link in this. The initial action that we add to the plan, it has no preconditions, but it has the positive effects which produce the initial state essentially. So, you remember that S is given by S1 up to Sn, and those same S1 up to Sn are the effects of this initial action. So, in plan space planning, the initial action always produces the starting state. That means these things are true. the final action has preconditions as the goal predicates or the goals G1 up to Gk, and it has no effects essentially. And these are the two actions that we started with essentially. And of course, this is not, this is simply says that if you are given a starting state and if you have given a goal description, then there may be many plans which can achieve that. We have not stated. So, in some sense, it is a set of all possible plans that could achieve. We also add this link that A0 comes before A infinity, or the first action is always before the last action, and this is shown by an ordering link here essentially. The initial plan pi 0 as we call it has no binding constraints and it has no causal links essentially. It simply states that this is a planning problem you are working with, but it is represented as a plan which is a kind of an empty plan. An empty plan also stands for the set of all possible plans, that there are various ways you can complete this empty plan. Now, there is a notion called flaw essentially. When is a plan a solution? Towards that, we define this notion of a flaw, and we see that a partial plan may have two kinds of flaws which prevents it from being a solution plan. One is open goals. Any precondition of any action in the partial plan that is not supported by a causal link is an open goal. So, if you look at, if you remember the initial plan that we saw, the pi 0 plan, then there were these goal predicates G1, G2 up to Gk, but they did not have any causal link supporting those goals. So, they are flaws, and the kind of flaws they are called open goals essentially. The other kind of flaws that a partial plan can have are threats. So, remember that a causal link says that AI produces P which is consumed by AJ. This causal link is said to have a threat if there exists another action, let us call it AT for T for threat, in the plan which potentially deletes P before it can be consumed. If that is possible, so the important word is potentially. It potentially deletes P before it can be consumed, then we have to do something about it essentially. So, there are two kinds of flaws, one is open goals, the other is threats. And the algorithm plan space planning basically systematically removes flaws from the partial plan that we have. A solution plan is a partial plan without any flaws. So, if you have produced a partial plan which has no flaws, then that is a solution plan. So, how do you resolve open goals? So, open goals are somewhere in the plan which are not supported by causal links. So, for an action to be applicable, its preconditions must be true, and if those preconditions are not true, that means it is an open goal. So, any precondition P of an action AP not supported by a causal link is an open goal. We have said that if there is an action which has a precondition and the precondition does not have a causal link, then you have to somehow provide a causal link for that essentially. So, a causal link for this proposition P. So, remember that P is an precondition of this action AP essentially. So, a causal link for P can be found in two ways. One is that there is an existing action AE. So, E for existing produces P, and it is consistent to say that AE happens before AP. AP is the one which wants to consume P, remember. Then you can add a causal link from AE to P to AP, and of course, then you must also add a ordering link. We have said that whenever we add a causal link, we must add a ordering link. So, in the extreme example where the start state is the same as the goal state, you can imagine that we would have started with an empty plan or pi 0, and because the start state has all the predicates that the goal state wants, all we need to do then is to establish those causal links from the start state to the goal state, and no new actions are needed. So, if an existing action provides a causal link, then you can just accept that. But if there is no such existing action, then you have to add an action. So, if no such action can be found, then we have to insert a new action, that is where planning happens. So, let us call it A new that we add, and that should produce P, because P is what we are interested in, that is an open goal that we are trying to resolve essentially. So, just add some action A new which will produce P and establish the causal link from A new to A P and an ordering link from A new to A P as well. So, these two approaches take care of resolving open goals essentially. Next, let us talk about a threat. So, let us say this is a partial plan that you are working with. There is an action unstack X something from A, and the important thing for us is that it produces this proposition clear A, and there is another action called pickup A which consumes this proposition clear A, because clear A is a precondition for pickup A essentially. So, we have this nice thing where one action is producing this predicate which is clear A, and another action pickup A is consuming that clear A, and these red arrows that you see are the ordering links. Let us say we have another action, it says stack B onto something. Now, we have not stated what you are stacking it on, it is some variable essentially. You can see that this action is a threat to the causal link that we have on the right hand side. Why? Because it is producing a, it's deleting a predicate called clear Y essentially. So, that is shown by saying that it has a negative effect essentially. And if that Y happens to be A, and if this action happens in the wrong moment, which means after unstack but before pickup, then it would have broken the causal link essentially. So, this action is a threat on that link that we have shown on the right hand side. When will this threat happen or materialize? If this unstack action happens before this stack action. So, if this is the order, if this is 1 and this is 2 and this is 3. Notice that we have not said that there is an ordering between these two, action 2 and some other action, but potentially if this is the order in which these 3 actions happen, that 1 happens first, then 2 happens, then 3 happens, then, and that is represented by the fact that unstack happens before stack and stack happens before pickup B. And also, if the binding constraint is such that Y is same as A, then you can see that this threat will come into play, and we use a term that the threat has materialized. So, an action A threat that can possibly disrupt an existing causal link AIP AJ is a threat to the link, and disruption will happen if all 3 of the following happen. A threat has an effect which is not Q, or negative effect which is Q, such that P can be, P is the predicate that we are trying to protect in the causal link, can be unified with Q. So, this notion of unification you might have studied if you have looked at logic, otherwise you can look up some reference including this book of mine mentioned here. In the simplest case, P is same as Q, which means A threat is producing minus P, and AJ wants to consume P, in which case if that happens to be the case, then potentially the causal link will be broken. We are still saying potentially because 2 more conditions are needed. One is that A threat happens after AI, and the other is that A threat happens before AJ. So, remember that AI is producing P which is consumed by AJ, and this A threat is threatening to produce not P, and if it happens before, after AI and before AJ, and the binding constraint is appropriate, then the threat would have materialized and it would disrupt the causal link. How do we resolve a threat? As you can imagine, there are 3 ways of doing it. To eliminate the threat, one needs to ensure that at least one of those 3 conditions is not met, which means you can undo at least one of them, then you are safe. The first one is called separation. It basically ensures that P and Q cannot unify, that variable, that whatever is there, if it is there in one of them, if there is a variable in one of them, that makes sure that the variable cannot take the value of the predicate or the block that you want to clear in this example. So, if you want to clear A and there is some delete clear x somewhere, make sure that x cannot become A. So, this is called separation. You are separating the 2 predicates by adding an appropriate binding constraint. So, you can simply say x is not equal to A. The other one is called promotion, which says advance the threatening action to happen before it can disrupt the causal link, and this can be done by adding an ordering link that A threat happens before AI. Remember, AI is the producer and AJ is the consumer of the predicate P essentially. The third one, as you can imagine, is called demotion. Delay the action A threat to happen after both the causal link related actions are completed, which means AI must happen first, then AJ must happen, and then A threat will happen. So, which is stated by the fact that AJ must happen before the threatening action has even come into play. So, that is the basic idea of planned space planning algorithm, and let us look at this example of resolving this threat. We saw that this is potentially this not clear y could break this threat, this example we saw. So, one way to solve it is promotion. You say that stack, this threatening action happens before this unstack action. So, it happens before both those actions, and remember that ordering links are from the first action to the next action. Or you can say that the last action, which is the consuming action, happens before the threatening action. So, that is called demotion. And the third one is to simply say that you want to say that y cannot take the value A, then this is no longer the threat essentially. So, next we will look at a small example and see how planned space planning works essentially. So, we will do that in the next video.